Welcome to this explainer. Today we're diving into something that really flips a massive assumption in modern science totally upside down. We're challenging this deeply entrenched, almost dogmatic view that if a blackboard isn't just entirely covered in insanely complex math, well then it isn't real physics. We're going to pull that apart and explore why a solid conceptual model of reality actually has to come before the numbers, and why leaning exclusively on math might literally be holding back our true understanding of the universe.
So this brings us directly to a really fundamental dilemma for physicists. Is it science or is it just philosophy? The modern scientific landscape kind of suffers from this profound crisis of categorization right now. Within current orthodoxy, the mere presence of complex variables is treated as the ultimate judge of what counts as physics. If you present a clear, mechanical explanation of how the universe might work, but it lacks some immediate algebraic derivation, well, it frequently just gets dismissed as philosophy. But is it, really? Or is it actually the foundational bedrock of a true reality model? The source material argues pretty strongly that math alone is simply not a sufficient metric for defining the boundaries of actual physical inquiry.
I absolutely love this quote from our sources. When we mistake the map for the territory, we risk endorsing models that are mathematically sophisticated, yet physically vacant. Really think about that for a second. Mathematics is the map, right? It's our descriptive tool. But reality, the actual physical machinery of the universe, that is the territory. By relying solely on symbolic complexity, we create a huge methodological blind spot. We end up prioritizing technical rigor over ontological truth. We get so obsessed with how beautifully the map is drawn that we kind of stop caring if it actually matches the real mountains and valleys of the physical world.
Okay, let's dive into this. We're essentially looking at two dueling ideologies here. On one side, you've got mathematics-first modeling. This relies super heavily on formula-driven descriptions and numerical outputs. But the risk here is immense. It often leads to this sort of pseudo-physics, where the numbers work out beautifully on paper, but they just don't describe actual reality. On the flip side, we have reality-first modeling. This approach demands an explicit ontological commitment, meaning you absolutely have to define the conceptual machinery and the structural behavior of reality first. If reality is essentially a physical machine that operates totally independently of our human symbols, then math is just a secondary tool. It's a powerful language for sure, but it is not the prerequisite for physical existence.
And leaning too hard into that math-first approach leads us straight into a massive strategic risk, the good enough fallacy. This is basically a state where mathematical success completely masks profound conceptual inaccuracy. Historically, this has been a huge problem for us. Scientists have literally tolerated physically wrong models simply because the math temporarily seemed to work. It acted like a mathematical band-aid. It allowed them to calculate basic things and maintain this temporary utility, all while remaining completely conceptually bankrupt about what was actually happening under the hood.
Now, this fallacy is incredibly dangerous in our modern era. Think about it. Today, if you ask a generative AI to produce an elastic space with specific properties, it can effortlessly churn out an endless sea of math and pseudomath. It'll give you incredibly complex generative variables that simulate behavior perfectly. But, and this is the absolutely critical failure, it will never find the actual physical structure or the true shape of the fabric of the universe. It produces the map without ever having seen the territory. It completely misses the specific structural machinery of reality.
So, to elevate a model from just being speculative conjecture up to accepted physics, it has to survive a strict, non-negotiable four-step gauntlet. Step 1, description. Does it actually map to observed behavior? 2, explanation. Does it have coherent analogies? 3, understanding. Is it conceptually accessible to the human mind? And finally, step 4, believing. Now notice the believing isn't just an arbitrary starting point. It is the emergent outcome of surviving those first 3 steps. Scientific acceptance can only happen if description, explanation, and understanding are perfectly aligned.
Let's look at what happens when these pillars fail. Take a look at this formula. E equals mc cubed. Yeah. If you confidently published a mathematically derived model that spit out that formula, you would literally be laughed out of the physics department. This right here is a categorical failure of the first pillar, description. A formulaic output that suggests a fundamental error like this shows exactly how disastrous a mathematically sophisticated yet physically incorrect model can be. If the math doesn't describe the basic reality we observe, it immediately fails step 1.
And here is a failure of the second pillar, explanation. Imagine we tried to explain the physical speed of light by simply saying, oh, well, it behaves exactly like the speed of sound. The explanatory dissonance there is just deafening.
I mean, sound requires a physical medium like air or water to travel through, right? But light travels through the vacuum of space. By using a totally incoherent analogy like that, we immediately undermine the physical credibility of the entire model. You just cannot pass the gauntlet if your explanations contradict the actual mechanical reality.
And this brilliantly illustrates a failure of the third pillar, understanding. There are models out there right now predicated on reality being a 10-dimensional structure, but conceptual accessibility is a non-negotiable requirement. Models that completely defy human cognition, things we just can't map to any structural reality in our heads, fundamentally fail the test of understanding. If we can't understand the machinery conceptually, we simply cannot bridge the gap to the fourth pillar. We can never actually reach a state of true scientific belief.
Okay, let's pivot for a second. Let's shift our tone from these philosophical criteria over to the purely mechanical. Let's get our hands dirty and see how this actually works. If mathematical formulas alone just aren't enough, how do we actually model a physical reality? Specifically, how do we model the actual structure of a fermion, one of the fundamental building blocks of matter? We are zooming in here on the highly complex reality model required to truly capture nature's structural shape long before the math even enters the picture.
Just look at the specific conjectural geometry required just to physically conceptualize a fermion. We are talking about utilizing Legendre polynomials, and hey, don't worry, there's absolutely no math test on this later. It involves a band trick-like distortion occurring within a torus-like inner volume, all completely encased in a ball-like symmetry, and yet the whole thing has to remain isomorphic to Euclidean space. It's a profound leap of structural insight. But the vital takeaway here isn't the complex vocabulary. It's that generative formulas alone cannot just pull this intricate machinery out of thin air. The conceptual shape has to be deduced first.
Contrast the mathematical tools we actually have against the physical reality we face. On one hand, we have general elastic space. For this, analytical formulae are abundant. We can describe general elasticity all day long. But on the other hand, look at two colliding fermions. When it comes to describing the intricate, highly specific machinery of two of these complex geometric structures actually crashing into each other, well, analytical calculus is completely unreachable right now. The formal calculation simply cannot keep up with the physical event.
Which brings us to a really massive conceptual gap in modern physics: discrete mathematics versus continuous nature. We pretty much only have discrete mathematics at our disposal, math broken down into distinct, separate values and points. But the reality of nature, the actual fabric of the universe, it's highly likely to be entirely continuous. There is a fundamental mismatch here. Describing a continuous nature with discrete math requires a tremendous amount of epistemic humility. We have to acknowledge that our mathematical tools have very real, inherent limitations.
So the crucial point is, how do we solve this? Well, we use what's called a tactical simulation. We take a discrete elastic network of points, which is something our math actually can handle, and we use it as a tactical bridge to simulate the continuum of reality. The physics here doesn't live in the mathematical symbols on the page. It lives in the conceptual machinery of the network being simulated. That is what allows us to compare it against the continuous reality we actually observe.
It really all boils down to this. A model devoid of mathematics is not automatically philosophy, just as a model devoid of a coherent reality model is not truly physics. Mathematics is an incredibly potent language, for sure. It provides rigor, exactitude, and allows for very precise communication. But the structural integrity of the reality model absolutely must come first. Without that conceptual machinery, the math is just a vacant map pointing to a territory that doesn't even exist. And understanding this directly impacts how we build technology and how we view our entire place in the universe.
Which brings us right to our final thought. Are we merely calculating the universe, or are we truly understanding its machinery? It's a pretty provocative question, and it really highlights the profound limits of human calculation when it's divorced from physical insight. Physical insight, actually understanding the specific shape and mechanics of reality, often outpaces formal calculation. As we push the boundaries of modern science, we have to demand models that don't just give us the right numbers, but actually give us the true mechanics of the universe. Thank you so much for joining me for this explainer. Keep asking those big questions.